Hello and welcome to Physics a Doctor. This is Dr. Gansham Tejani and let's start. Class 11, chapter number 9, Mechanical Properties of Solid. And the similar content is covered in JEE NEET unit number 7, Properties of Bulk Matter. And this is session number 1, Stress Strain. So in this session we'll be covering stress strain, tensile stress, compressive stress, and how by solving various examples of JEE, NEET, JEE Advanced, and other examples. So let's start. You might be wondering that what kind of mechanical properties are we going to learn? So it is like that. See, you can see on the left hand top corner, if you see, there is something, some object which is expanding. See, when we apply a force, what happens? There is increase in length, it is to be seen. You can see the similar, you can do the experiment on a spring. If there is a spring and if we push or pull the spring, what happens? There is a change of length inside a spring, isn't it? So that we are talking about, that if we apply some force and there is some change is to be seen on a body, and therefore we can say the solid bodies are not perfectly rigid in reality. We have assumed so many times previously that a rigid body, but in reality, almost all the bodies are having some kind of deformation, some kind of change in terms of shape, in terms of length, and therefore these are not rigid bodies perfectly. And therefore, we are going to study the properties, how it works. So we can see the animation, it was shown here on the top side. The initial condition was where it was object was a small, it was like this shape, this much size and the shape. And when the forces are applied on the both the side, so it expanded. Don't you think that the behavior of this object is looks like a spring? Of course, it is a behavior we can consider like a spring only. And so bodies can be stretched, compressed. We can bend a body also. It is also possible that we may bend the body. Of course, we can extend, we can stretch, we can compress, and we can bend. These all are possible in the real sense when we talk about objects, of solid objects. So if we stretch a helical spring, if we just take an example of a spring, let us just draw a spring. If you compress this spring, what happens? Spring compresses. Or if the similar spring we pull on both the opposite sides, so what happens? There is an increase of length that is seen. And we know this properties very well. So when we leave the end of the spring, right? So example, for example, if this is a spring and if we apply forces on both the sides, what happens? There is an increase. There is an increase of spring length. But if we remove this forces from both the side, what happen? It return to its original shape and size. And here we are talking about some property. Because of what? Because of what this happens? Think and answer me. See, this is the property we are talking about, and that property is known as elasticity. You might have heard this word elastic. Usually, we call a rubber a property like a rubber, which we call it elastic material, right? We can stretch the material, that we call it elastic material. We use many a time. Many a places we use elastic material, especially in clothes. We used to use this elastic materials. So here the property like that when we apply a force, right, on a top animation we have seen that when we apply a force, what happens? There is an expansion. There is an expansion of a body. There is an expansion of a body. And once we release this force, what happens? The body return to its original position, means original shape and size. That property is known as elasticity. Definition says that the property of a body. So this is a property. This is a property of a body by virtue of which it tends to regain. It tends to regain its original shape and size when applied force is removed. When applied force is removed, this is known as elasticity. And deformation, that means what? Is the change of its shape, change of shape, or you can say increase of length. If you see here, the previously the shape was only this much size, but with the increase of force there is an increase in length also. So that increase of length we just denote by delta L, and that is known as elastic deformation. That is known as elastic deformation. And see, a plasticity, there is an opposite property of elasticity, that is known as plasticity. You just, as of now, you just learn what is meaning of the plasticity. We will have a detailed discussion on it. So plasticity, it is a property of material to retain change its change shape and size after loads are removed. Say for example, the similar example, the top on that object, suppose after stretch, this is the length, say for example L prime, and if we remove this force from the both the side, and suppose it remain with this final L prime size, that means this behavior is known as a plastic behavior. You must have experienced, if you stretch a plastic, what happen? Plastic changes its shape. We can change the shape of plastic by stretching this up to some limit, and that refers to plasticity. So it is exactly opposite property of plasticity. In case of elasticity, what happen? It return to its original position. It return to its original position. But in case of plasticity, the thing, it is not possible. In the case of plasticity, it retain its final shape. So we have taken example of a spring. Say for example, this is a spring. This is a spring which is having some length L, and if we apply force on this spring, what happen? It compresses. It compresses. Yes or no? It compresses. You can see there is a force. Say for example, it is applied F, and there is a decrease in length. There is a some decrease in length. So there is a change of shape. But if I remove this force, what happen? Again, spring rebound, and it goes back to its original shape and size. That property is known as elasticity. Another, you can see example, there is a, if the similar spring it is expanded, if we apply forces on both the side, to full forces if we apply, so what happen? There is an increase of length. There is an increase of length, delta L. There is an increase of length, we can call it delta L. And if we remove this applied force, what happen? Again, spring will return to its original position. But suppose if we expand this spring up to, or you can say beyond certain limit, what happen? You know that property of the spring, because of that it may not return to its original position, and that comes under plasticity. And we have done this kind of experiment many a times, and the similar things I'm explaining here. So see why this kind of study is required. We just talk about two properties, one is elasticity and the plasticity, right? We will be having more studies also. But see why mechanical properties are required. See, there is a first drawing you can see here. There are household items, kitchens items are there. If you want to manufacture this, or maybe other than whatever, right? If it is a metal product, a non-metal product, whatever. By studying these properties, we can produce these items. Even we can produce a bike. Why not? It has so many parts, a metallic, a non-metallic, right? And possess this kind of properties. It may possess elasticity or plasticity or maybe other properties. To construct this bike, right? So I can drive this bike from 1 to 100 per hour in 10 seconds. And for that, I have to understand the material property. Otherwise, my bike may fail or I may fail face accident also. I can build a factory also. There are large number of equipments, there are number of robots, maybe machines, supply chain, whatever, right? See, and that is the reason that we have to study mechanical properties so we can design, we can manufacture in a day-to-day life. Let's have one more. The elastic behavior of a material plays an important role in engineering design, not only in engineering design, but it is also usually applicable in the medical field also. For example, while designing a building, if you are a civil engineer or an architecture, your role is to construct buildings, design a buildings, yes or no, maybe a Burj Khalifa or next Burj Khalifa. So you must be having a property in your mind that you can utilize in a best manner. So knowledge of elastic properties like materials like steel, the buildings are having steels, concrete, it is required essential. And the same is true in the design of bridges, automobiles, ropeway, medical equipments, rocket, aeroplane, etc. You name the field where we are not using metals, we are not using steels, we are not using concrete. Mostly everywhere. Even if you talk about medical, so we are utilizing different properties, different items, but most of them are solids. And for that also we need to study mechanical properties. So, see, we can have several questions in our mind and we can answer them. Like, can we design an aeroplane? Can we design an aeroplane? Of course, aeroplane design is a difficult task, but of course, we can do. And we can have certain conditions. The aeroplane should be light, means weight of aeroplane should be low, so we can have better efficiency, and but sufficiently strong. So, there should be no failure for the aeroplane. We can have one more question. Can we design an artificial limb? You can see for the medical personnel, they are not just inside the clinic or they are just not a doctor who check the patient, but their role beyond that, they are also researcher. So we can construct this a stronger limb for a medical purpose. Why does railway tracks have a particular shape like I section? You must have seen the railway tracks and it is having this kind of I shape. It is not T shape, not a rectangle shape, but why there is a I shape? You can find this answer by studying these mechanical properties. Why is glass brittle? Means it breaks. You must have seen this kind of glass, broken glasses, several places, right? And why it breaks? It has some property, brittleness, and why it works. So all of these questions you must be having in your mind, and the answers are here, right? So answer to such questions begins with the study how relatively simple kind of load or forces act to deform different bodies, and we are studying this now. Let's have again elasticity. We studied elasticity. Let's again recall. So it is the ability of material, or you can say property of material, to regain its original shape and size after removal of external force. So elasticity, what is elasticity? It is ability of material to regain its original shape and size after removal of external force. So a body which completely regain its original shape and size after removal of deforming force is said to be perfect elastic. If I compress a spring, and after removal of the force, if spring bounce back to its original shape and size, it is known as perfectly elastic body. And what is plasticity? It is again ability of material to retain. See, this is the word where there is a change. It is a retain. So it is not coming back to its original position, but it is taking its final position. Whereas in the previous case, it regain, or you can say it return to its original position. Right. So these are the two properties we can see, and let's see here the animation. Let us understand the concept of elasticity by using an animation. Let's just watch first. Let's watch again. So we are considering a spring. A spring we have seen when we apply force, maybe in the downward direction, so there is a compression. If we apply force on the upper direction, there is an expansion. And that force, it is known as deforming force. Deform means there is a change of shape. But if we remove this force, what happens? It return to its original shape and size, and that is known as elasticity. And that property is known as elasticity. But you note that, see, there is no possible to have a perfect body which can have perfectly elastic body or a perfectly plastic body, right? So you note that if there is some question like that, a body returns perfectly in the NEET or JEE, so you have to remember that word, that it is not possible that no material of body can be perfectly elastic or a perfectly plastic. Now one more, what is stress? What is stress? See, we understand elasticity, that means it's the ability of material to regain its original shape and size after removal of force. And for the plasticity, it's a property of material to retain its final shape and size after removal of external force. Fine. So, see, we are now talking about stress. Now we are talking about stress. What is stress? So, it is called a reaction force or restoring force per unit area of body, which is called into play due to action of applied force called stress. Don't worry about definition. We know that as per Newton's law, there is always equal and opposite force if it is applied on it. Yes or no? So, say for example, if the body which is here having some length L and it was stretched because of some pull forces on both the side F. So, what happened? There is some increase of length. We can see if there is some sufficient force which can apply. So, we can see there is some increase of length of this body. See, but this increase is always opposed by internal resistance, or can say internal moleculars. So we know that when we stretch any rubber, what happen? When we stretch a rubber, so rubber is also equally trying to return to its original position, and that is resistance, or you can say reactive force. So as per Newton's law, there is always equal and opposite. Reactive force is always present in a body, and that is always opposing that whatever we applying force on a body. Of course, there is a change of force if we apply, but once we relieve this force, what happens? That reactive body or reactive force or restoring force per unit area, it it try to it make it object return to its original position, original shape and size. So this restoring, you can say force, restoring force is known as stress. This restoring force is known as stress. It is denoted by sigma. It is denoted by sigma. So here, if the body is stretched by two equal and opposite normal to its cross sectional area, the restoring force per unit area is known as tensile stress. If we apply two pull forces, right, on the both the side, if you pull, so there is an increase of length. If we right apply pull forces on a body, so there is an increase of length. So load is known as tensile load. This load is known as whatever we are applying here, P or F force outward direction. That load is known as tensile load, and the whatever stress is generated inside a body, that is known as, we can define sigma T, or simply we just write sigma. That is also okay. So that is known as a tensile stress. So by providing pull on both the side, or maybe a single side, I will also come to that point also, that is known as stress. Now, so if the body is compressed, so similar body, and we apply on both the side compression load which is going inside. So if the body is compressed under the action of applied force, restoring force, or you can say reaction force, what it try to, it will try to pull this body outside, or it opposes, as per Newton's law, it opposes whatever external force it is applied. So see, this force, it is known as compressive force. This force is known as compressive force, and whatever stress generated inside this body, it is known as compressive stress. We can denote by sigma C. We will come to this point once again also. Don't worry at all if you have some confusion. So in before go to this statement, see, we have understanding for the elastic material. Elastic material, that means what? A material that we can stretch, a material that we can stretch. Say for example, this is simply a rubber. Let's just consider a rubber. So when we apply two pull forces on both the side, two pull forces on the both the side, what happen? When we apply pull forces on both the side, so rubber, it's a elastic material. So there is an increase of length. Yes or no? So see, we assume that if rubber, it can have more elastic property, higher elastic property. That means what? It stretch higher, it stretch more, it stretch, right. So if we can stretch an elastic property, elastic material at higher extent, at higher level, that we assume, that we consider that it is having more elastic property. But see, for the engineering purpose, for mechanical properties, this is actually not true. So what in daily life, we feel that a material which stretch more is more elastic, but this is not true. This is not true. See, this kind of questions we had seen in the NEET and JEE examination also, and therefore understanding is very much important. So, right. So this statement is misleading. It is actually wrong statement as per engineering point of view, or you can say mechanical properties. In fact, material which stretches to a lesser extent, material which stretches to a lesser extent for a given load is considered to be a more elastic. Might got confused? Let's have an animation and let us understand how it works. So in the animation, you can see there are two strings. One is rubber string. One there is a rubber string, and you can see there is a steel string. We know that rubber and string property. Both are there, and both are having some length L. Both are having some length L, and both are having equal diameter. Both are having equal diameter. So we know that whatever stress is there, so we know that in general stress is sigma is equal to applied force divided by cross sectional area. This is equation of tensile stress as well as compressive stress, the common equation both are having. Now, so here we have rubber string and second is a steel string. So which one is more elastic? This kind of question was asked in NEET and JEE also. Which one is having more elasticity? So as an ordinary, we always think that rubber definitely we can stretch more with the force similar applicable application. But if we want to stretch a steel, majorly it is impossible. See, every material having a properties like elasticity. That means you can stretch every material. Of course, for a steel, you need much larger force compared to rubber. But yes, steel can stretch. We will prove that part. Don't worry. So here, rubber, if we apply equal and opposite forces for both the cases, what happen? What happen? See, rubber can extend higher level. Rubber can extend up to higher level. Yes or no? Rubber can be stretched up to higher level, right? Rubber can stretch up to higher level. You can see also from the animation this increase of length. We can say L is original plus increase of length delta L is much higher compared to the steel body. Yes or no? This is much higher compared to steel body. But see here, once we take this load, that means once we remove this load, what happen? Once we remove this load, steel return to its original position much quicker. Steel return to its original position much quicker, and that is the reason that steel it is to be considered. Steel is considered as a more elastic. Steel is considered as a more elastic, not rubber, not rubber. Even you see here, it is equal to force per unit area. It is stress. It shows capacity. Just it shows capacity. It shows its stretching capacity up to what level we can stretch. So it is a sigma is equal to force divided by area. For the similar area, we need much higher force compared to it's a rubber compared to rubber. So see, say for example, if we apply 1000 Newton, so still definitely it will stretch. It can withstand 1000 Newton load. But if we apply 1000 Newton to the rubber, what happen? It will expand. Definitely delta L will be higher, but it will fail. It will break into the part, and therefore the you can say property, property of elasticity. It is having better in the terms of steel, not in the terms of rubber. We can see again here rubber string. We are having both are having equal area. Area is equal for both the cases. Length is also equal for both the cases, and we are applying equal and opposite force. Right. So here, because of that, what happened? Of course, elastic material is having higher stretch. It is having higher stretch, right? Rubber is having higher stretch compared to steel. But see, elastic property, it shows the material strength. It shows material strength up to what load it can take, force divided by area, right? So up to what maximum load it can take per unit area, right, to get a deformation. That's why steel is more elastic. It can take much more load compared to rubber, and ultimately see a stress. It shows a strength of material, right? Elasticity, if you consider here, it is not a measure of what amount of deflection is possible for the body, but here elasticity, it is a measure which represent stress, and stress is a measure of capacity of material, up to what level this material can take. And that's why the answer, if you are thinking, that is may not be, or it is not correct in terms of property of material. So let's jump into examples. Here is example number 1. So there are statement. So statement 1, it is given here: when a material is subjected to a tensile or stretching stress, we know that it is sigma n is equal to force divided by area. See this equation, you just remember this equation. We will be utilizing this equation again and again. So statement 1, that when a material is subjected to tensile stress, or you can say stretching, the restoring force, right? We know that simply it is the internal resistance of a body. When we apply force here on both the side, so what happen? Material increases its length, increases its length, and this is opposed by restoring force, and that is restoring force. We know that that is known as sigma, or you can say tensile stress or compressive stress, and which also refer to material's capacity. So here, tensile stress, the restoring forces are caused by interatomic reaction. See, we have not studied this part yet, but let me explain here. So we know that all the materials are having different molecules. They are having different molecules, and these molecules are having attraction, and in such a way that when this is in a rest, or you can say in equilibrium condition, that means this attraction, it is having attraction, or you can say there is a uniform, or you can say equal gap, or you can say equal length, or equal distance between two molecules, that is measured. So when we stretch this material, what happens? There is an increase of gap. So initially, if we just take only two molecules, let us just consider very few molecules. So say for example, initially before stretch, this gap between two molecules, it was, and because and it has attraction between this. And when there is you can say there is a stretch, or you can say increase of length. So if there is an increase of length, the molecule also go apart. Say for example, up to this level, so gap increases. So what happened? This body try to return. The molecular try to return to its equilibrium condition. Yes or no? And because of that attraction, it is always there between molecules, and that attraction cause internal resistance, or you can say restoring force. That is because of it has a restoring force, and this restoring definitely cause of a material is subjected to tensile. So yes, statement 1 is definitely true. It is true. Statement 2 says that a restoring force is called into play in an elastic material. by inherent property, by an inherent property. Definitely, restoring is inherent property of material. Every elastic material is having inherent property which restore. Yeah, fine. The half statement is true. Let's read the remaining part. So it is mentioned of the material and not and not due to interatomic attraction. See this property, the property we know that there is some cause behind the property. And what is the cause behind this property? See, you have certain property, but there is some cause. If temperature flows from one point to another point, so we cannot say that it has a property to, you can say, move temperature from one point to another point. It is not like that. It is definitely a property, but it is property of some molecular movement or some other property. Similar here. So it is a property of material, but it is because of what? It is not, it is incorrect, and it is due to interatomic attraction. Right. So first statement is true. First statement is true, but second statement it is incorrect. Second statement it is false. So for the one that is statement one is true, yes. Statement true is true, no. So one that is incorrect. B, statement one is true. Statement two is true, no. C, statement one is true, yes. Statement two is false, yes. Answer is C. Answer is C. The correct choice is C. So what is our explanation? When the material is not subjected to any stress, we already seen this is our body without any load, and let us just take two molecules, imaginary molecules having this distance and having attraction, right? It try to retain its position every time. Then when a tensile stress is applied, that means a load is applied, we are applying full force on both the side, and because of that there is an increase of length of the body. And similar happens to what? Similar thing happens to this molecules also moves apart. But see, to every you can say material or everything always go back, like to go back to its equilibrium condition. So what happened? This molecules opposes this force. This molecules opposes this force and try to return to its original position. Right. So here it becomes separation, and the interatomic force is attractive, and this force provides the restoring force under which the material regain its original shape and size when stress is removed. When stress is removed. Say we have seen this video previously also. So a rubber string, it is having equal diameter we have taken and having equal length and having equal force it was applied. So when there is a force is increased, when there is a force is increased, let's see one moleculus it is here, second moleculus it is. So initial moleculus it was here. When there is an increase, so moleculus may reach to another level, and it try to return its original equilibrium position, right? And therefore it is having, you can say, interatomic or intermoleculus attraction, right? And we know that steel it is having higher capacity, it is having more attraction, compared to rubber, and therefore steel is having more elastic property compared to rubber, right? So here when the deforming force is applied to a body, it reacts to applied force by developing reaction, or you can say restoring force from the Newton's third law is equal in magnitude and opposite in the direction to the applied force. Now next is compressive stress. We have one question from compressive stress, but before that, let us again recall the compressive stress. So we know that suppose this is a body. Let's make a better body. Suppose this is a body is having any shape. Maybe let's do this time three-dimensional body. If we apply some force, compressive force, if you just take a rubber, right, eraser on your hand and you compress this eraser, what happens? There is a decrease in length. There is a decrease in length. We can see there is a decrease in length of rubber. Yes or no? And because of that, what happened? Intermoleculars, it try to return to its original position and it opposite this load. It is a reactive forces, or you can say resistive forces. We know that by using compressive. So it is equal and opposite phenomena of tensile stress, and the equation is similar: force by area. So if you are calculating tensile or compressive, whatever, there is no difference in terms of mathematics. Mathematics treat both are equal. So we have again example number one more example. Example number two. Statement one says that when a material is subjected to a compression stress, a restoring force are caused by intermolic repulsion. Now, we have seen this in the case of tensile. If it was true in the case of tensile stress, that means it is also true for the compressional stress. So we have seen this. Say for example, this is our rubber, and initially it is having two molecules at this position. After compression of this rubber, say for example, shape of this body, it compress up to this level. So here there is some effect on molecules also. It compresses to this level. So what happens? This molecules wants to move it to its original position, and this apply opposite force. That is sigma, and that is a restoring force. So statement one is true, right? Let's see statement number two. The atoms of material never repel. See, repel, that means it's a returning. It's a returning, right? It's a intermolecular repulsion. See, we have seen the in the first case itself, it is having repulsion. It is having returning. It is having reaction. So statement two is false. So we have here. Let's just erase this all. So statement one is true. Yes. Statement two is false. One is true. Second is not true. False. Statement 1 is true, statement 2 is false. Yeah, this C is correct. C is correct. D need not to check. So answer C is correct. See, intermolecular repel, or you can say intermolecular attraction. It is always there and it always react. So when the material is not subjected to any stress, it its atoms are in the normal equilibrium position. We have seen this by drawing this object, right? Initially it is having intermoleculars like that. After compression, there is a reduction in the length, and moleculus also contracts. And moleculus wants to go back to its original shape, original position, right? So here, distance between moleculus decreases, and it wants to go back to its original R, and therefore it repels. So when the material is subjected to compressive stress, cause an interatomic forces is repulsive, which cause restoring force. Example number 3, a zero point 0.4 meter long copper wire. So see here, let's just draw a copper wire having some diameter, having some length. This is copper wire having equal diameter. Just assume that it is having equal diameter. So zero point 0.4 meter, this is 0.4 meter, that means it is given length. So we can see this is a copper wire and it is having length L. So a 4 0 means 4-meter long copper wire of cross section. That means area. See, cross sectional area, that means it's a, if you cut this object, so we can see there is a circular shape. If you cut this object from here, so it is a circular shape. This cross sectional area, this is area. This is area. We call it A. So cross sectional area, it is having A, and it is given A is equal to 1.2 centimeter. If it is given in centimeter, we need to convert this into meter square. So 1.2 centimeter square. So what is 1 centimeter? Can I say 1 centimeter is equal to 10 power minus 2 meter? That means 100th portion of meter. Yes, we can see. And if it is square, so we need to have square of 2. That means here minus 4, not plus 4, right? It become minus 4. So we can convert this into meter. So A become 1.2 multiplied by 10 power minus 4 meter square. It is stretch. That means stretch means there is some force, outside force. It is full force is applied. Let's have another color, purple. So it is, there are two forces are applied on the both the side. Say for example here F, we know it is F, and in this side also F. So it is stretched by force. It is stretched by force 4.8 multiplied by 10 power 3 Newton. So F is given 4.8, 10 power 3 Newton. So it is asked, stress will be, what is stress? What is stress will be? Option A is given 4 multiplied by 10 power 7, B is given, C is given, and D is given. So there are options are given. So let's solve this example. So here given data area, we already identify area is equal to 1.2 centimeter square. We need to convert this into 1.2 multiplied by 10 power minus 4 meter square. When we got this conversion, then second is force is given. What is force is applied? 4.8 multiplied by 10 power 3 Newton, and also we have length. Also we have length. Also we have length. Fine. Now, so we need here to have stress. What is equation of stress? What is equation of stress? Stress we know defined by sigma, and it is force per unit area. Sigma is equal to, stress is denoted by sigma and is equal to force divided by area. Is force given? Is force given? Yes. It is 4.8 multiplied by 10 power minus 10 power 3. And is area given? Yes. 1.2 multiplied by 10 power minus 4. So we can say here bar 12. So it becomes 4, and this is minus 4. So it goes up. So 3 plus 4, it becomes 10 power 7. So we have answer. This is A, 4 multiplied by 10 power 7 Newton per millimeter square. Isn't it very simple? Of course, it is very simple. So answer number C, and A and C, maybe there is some error in this case also. So A and C both are equal, right? Maybe typo error may be there. Fine. So here example number 4. What are the dimensions of steel? See, we studied this in our chapter number 2, how to take dimensions, how to get dimensions. Now let's erase this all the things first. So we know that stress sigma is equal to force by area. What is unit of force? It is Newton. And we know that force is equal to mass multiplied by acceleration. What is unit of mass? It is kilogram. And what is unit of acceleration? It is meter per second square. Yes or no? So here we can write also kilogram meter per second square, and here become 1 upon meter square. So 1 meter should be cancelled. So we got it. So Newton per meter square kilogram, and this is kilogram. 1 by second square 1 by. So what about kilogram? So it becomes kilogram. We know that kilogram, for the kilogram, tell me, m 1. Then for the length, meter, so we have 1. And what about time? We have time. So it is 2, but minus. So dimensions is equal to m 1 l. It is see here denominator, so it should be minus 1, and it is stays minus 2. Example number 5. A wire breaks when subjected to a stress. So we know that stress we use sigma, and here it is some value is given up. It is a value of sigma is s. So let us just draw a wire. This is a wire or road. We can call it road, right? Wire. It breaks when subjected to stress. Sigma is equal to s. So we know that when there is a forces on both the side, so there is a internal resistance, or you can say a reactive force, which is called, we call it as a sigma, and applied both the side, it is having force. So it is a level. You can say when sigma become as, it is mentioned that wire breaks. This wire breaks. So it is ultimate condition is given for this wire. So it breaks maybe anywhere. And see, maximum limit of sigma it is to be considered that wire should not break. So it is a breaking of wire that is considered as a S. So here only sigma and S are considered as equal, and it is maximum level of sigma. So here mention if rho, we know that what is rho, that is a density, it defines the density. So it is having, material is having density. So rho is a density of material of the wire, and g is acceleration due to gravity, then length of the wire. So that it break by its own weight is. So we need to again redraw this. We need to redraw this object. Let's see. And we can put this in the vertical terms. Otherwise, it may not break. So here, this is our wire. And here, top the side, let's say it is fixed. And because of this self weight, it is having self weight. It has some mass m. It has some mass. Let us call m. And because of gravitational, there will be must force. What we can quote, F is must be is equal to m g. That body is having mass mg into downward direction, and it is having density is having, material is having density rho. So do we have its mass? Can I say mass is equal to density multiply by volume of a body? Can we say mass is equal to density multiply by volume of this body? So if this body is having, maybe say for example, it is having a radius r and length l, so we can find also volume. But we are not going beyond that. Fine. So we know that stress is equal to sigma is equal to force by area, and it is given here. Here it is given maximum. So at which level S become maximum? So S is equal to F by A, and what is load of this road? It is having a self weight. It is having a self weight, and we know that self weight is equal to mass multiplied by gravity. Self weight is equal to mass multiplied by gravity. So we can put S is equal to F divided by A. S is equal to F by A. F is equal to mass multiplied by gravitational acceleration. So it's a gravitational pull. We got it. So F is equal to mg by A. Now what? So we know that m, we already seen density multiplied by volume. Density multiplied by volume. And if I want to have this road volume, can we find this road's volume? Yes, it is having, say for example, it is having not r radius, but let us just take, it is having area A. The road is having area A and having length L, having length L. So can we put here rho, this is area A, L, mass is equal to, can we put this here? So here S is equal to rho A L, we can say area, we can remove this area, we can remove this area, right? So we have S is equal to rho L G, and what we need here, we need length of wire, we need length of wire, so we can take length into power. So S is equal to rho L G, we can put length into power, so L is equal to S by rho G. Which answer is correct? D. So answer number D is a correct answer. So we have example from JEE Main 2019, and the example is the elastic limit of brass is 379 megapascal. What is mega? What is mega? Mega means 10 power 6. You have to remember this all, right? What is kilo? Kilo is 10 power 3. What is giga? 10 power 9. Yeah, you know it. Wow, great. So see that you know how to convert this giga, mega, and this also mega. That means 10 power 6. What is Pascal? What is Pascal? Pascal, it is equal to Newton per meter square. Pascal is equal to Newton per meter square, right? So here elastic limit. See elastic limit. See again, let's go back to our fundamental elasticity. That means it's a property of material. So when there is a forces are applied, when there is a forces, say for example, F is applied on the both the side. So material opposes this applied force, and that resistance, or you can say reactive force, that is known as stress, and that is also known as elasticity, or that is known as elastic limit. Means it's maximum limit, it's a maximum limit at which material may fail. It is, so we have here sigma, so this value is given as a sigma. Elastic limit of brass sigma is 379 megapascal. 379 megapascal. What should be the minimum diameter? What should be diameter? Diameter of this brass rod. Brass is a one metal lamp. If it support, that means it is having force 400 Newton without exceeding this limit. That means it should not exceed this limit. It should not exceed this limit. So what should be diameter? See, see here. This is a design problem, right? So here we need to identify what is diameter. What should be diameter so the material should not fail. So here given data, we know that given data, elastic limit, it is also we can call it as a stress limit. Sigma is equal to 379 megapascal. Here given data, the data is given. So elastic limit, it is given 379 megapascal. So we can put sigma. Elastic limit, that is sigma. Sigma is equal to 379 megapascal. Can we convert this sigma? 379 multiplied by 10 power 6 because of this mega, and pascal, that become Newton per meter square. So stress is equal to sigma is F by A. Stress is equal to sigma F by A. We need here area. We need to find area, that means diameter. So we can move this area on the opposite side. So area is equal to force by sigma, and here this is object is given diameter. Object is having diameter D. That means its shape cross section is circular. object shape is circular, and therefore this area is pi by 4 d square, or we can also write pi r square. So let's put here a is equal to pi by 4 d square. What is value of f? F is given 400 Newton, so it is 400 Newton, and sigma is 379 megapascal. So 379 multiplied by 10 power 6. So d square is equal to opposite side. You can convert this, and you can find d is equal to 1.16 multiplied by 10 power minus 3 meter, and diameter we usually convert in terms of millimeter because it's having a smaller value. So d become 1.16 millimeter. So is it correct? Yeah, C is the correct answer. So that was the simple question was asked in JEE 2019. But if you don't understand this elastic limit, that means it's a sigma. It is a sigma. So you may lose the marks. It is not always it is not like that always it is written like a stress. It may have elastic limit, or it may have a maximum limit, or it may write yield limit. All are similar. So answer C is the correct answer. We have example number 7, and again it is from JEE main. A steel wire having a radius. So it is given, radius is given. We can write radius is equal to millimeter. You can convert this into meter. So it becomes 2 multiplied by 10 power minus 3 meter. Carrying a load. Load, that means force. So here 4 kilogram given. So we can take M, carrying a load of 4 kilograms. So mass is 4. Is hanging from a ceiling. Oh. Let's just draw it. Let's just create, say for example, this is our ceiling and this is a road, a steel wire. It is having steel wire. It is having a radius is equal to 2 mm, and it is having load, and it is taking load. Say for example, it is having a load 4 kilogram. Is hanging from a ceiling. Given that, see, G is now not 10 here. So G, gravitational acceleration, G is equal to 3.15. Oh, good. What will be the tensile stress that would be developed in the wire? See, the question is asked that, see, when there is a increase of length, when there is an increase of length after application of force, so under stress is generated inside this tensile, right? So here in this rod, in this wire, whatever stress is generated, it is resistive stress. It is to be tensile. So we need to find stress sigma. We need to simply find sigma. Let's solve it. So we have option 6.2 10 power 6 Newton per meter square 5.2. That means uh, we can say the 10 power 6 is common everywhere, but 6.2, 5.2, 3.1, and this we need to identify, right? And 4.8. JEE 2019, the main examination, this question was asked. So we have that radius is given, r is equal to 2 millimeter. We can convert this into meter. Mass is given 4 kilogram. So we need to convert this into force, and force is equal to mass multiplied by G. We know that very well. And G is given 3.1 Newton. And what is sigma? What is sigma? We need to identify sigma. Do we have equation for sigma? Yes, stress is equal to force by area. Is force given? Mass multiplied by gravitational acceleration. So it gives us force. And what is area? So here see, road is given radius. Here it is steel wire, and wire is having round shape. It is given radius. See, if it is given radius, that means it is round shape. And this sectional area is equal to pi r square. So we can put here pi r square. Put the values. M is equal to 4. G is equal to 3.1 pi. Don't take 10 here because G is given 3.1 pi. So pi should be cancelled. Pi should be cancelled. 2 multiply by 10 power minus 3. So 2 become 4. So 4 is cancelled. So 10 power minus 6, if you don't calculate, you can get 3.1 as a correct answer. So C is 3.1 is our correct answer. So answer number C is the correct one. We have one more example number 8. One end of a uniform rod that means a bar of a mass m, mass is given, and a cross sectional area a, oh, area is given, is suspended from a rigid support. Say for example, this is having a bar suspended from a rigid support, and it is having mass m, right, and having also cross section area. If we cut this section, so it is having area a. So suspended and equal mass m. See here, there is a one more twist. Something is given additional. One end of uniform rod having mass m. So this mass of rod is m, and cross sectional area a is suspended from a rigid support, and an equal mass is suspended from other end. Equal mass is suspended from the other end. That means one end is fixed, opposite end is having some other mass. Say for example here, and that is also having m. Ooh. The stress at the midpoint, that means midpoint of the road, that means here, say for example, this is having length L, stress at the midpoint. So this is at L by 2 distance from the top. We need to find here stress sigma. Oh, good question. So we need to find, options are given, 2 mg by A, 3 mg by 2A, mg by A. So we have stress sigma is equal to force by area. We need to identify force at this particular junction. At this position, what should be force? See, we know that first it is a mass. So for this mass, it is m multiplied by g for this bottom. And see, half of the mass up to this region, only this half of the mass is subjected to stress, because upper part is not providing support for the below part or intermediate position. So here for the half, mass should be half. The bar is uniform, so the total mass of the second, it was half, so it should be m by g and multiply by g. So it is a gravitational acceleration. So we have mg plus m by 2g is equal to, what is equal to 3 mg by 2. You got answer. See here, 2 3 3 3 something it's there. So here, weight acted at a midpoint is equal to weight suspended mass plus weight of half of the road. We have seen the similar case, weight of the suspended mass, that is m, and half of the road, that means m by 2. So is equal to mg plus mg by 2 is equal to 3 mg by 2, that is force. So now stress is equal to 3 mg by 2 divided by area. So sigma is equal to 3 mg by a 2a. So which one is the correct one? B, 3 mg by 2a. So answer number B is the correct answer. Very simple question, and this kind of simple questions will be there in the examination of JEE and NEET. So be ready for that. Oh, one short boy and tall man, or both are men. I don't know. That's your question. Oh, example number 9. Again, it is JEE 2009 17 main. A man grows into a giant. Oh, you must have watched movies of giants. So, man, this is a man, this is a man. Grows to a giant. A man grows into a giant such that his linear dimension increases. See, only single dimension increases. We have, if we talk a volume about that, any object, so there are different parameters. One is, you can say, height, width, or length. There are three dimensions are there. But see here in this case, it is clearly mentioned that His linear dimension increases. That means only single dimension increases. Not all the dimensions are not increasing. Only single dimension increases. Let us increase his height. Let us just increase his height increases. Let us assume that a man's height increases and he becomes giant, tall, without increasing its area. Assuming that his density remains same. Another part is given density. There is no change in the density, so he is as denser as the previously. Can you answer that? Because of this increase of length, will he has more mass than the previous one? Will there is an increase of mass? Comment your answer below. So here density, there is no change in the density, there is no change in the density, and the expansion, it is just a single dimension expansion. So the stress is in the leg, stress is in the leg. So whatever load, it is just asking load per unit area. Whatever load on the leg or simply compressive stress. Is it a compressive or tensile? It is just erase this. This is not tensile. It is compressive stress. So stress in the leg will change by factor of what? JEE 2017 main. 1 by 19, 18, not 18, 81. C is 1 by 81. D is 19. Good question. So we know that stress is equal to force by area, and simply force is equal to what? Weight of man. Weight of man divided by area. So if we take the cross section area, if we just imagine this person like it is having this kind of shape. So the bottom section, let us understand, let us just assume a square section. It leg is just having a cross section having length L and width, say for example B, and it is having, the person is having height H. See here. So we know that sigma is equal to W, that means mass multiplied by gravitational acceleration. And what is mass? Mass is equal to density multiplied by volume. And what is density? Density is constant, density is not changing, but volume is equal to L B H. Can I say LBH? Out of LBH, only one dimension increases. Say, for example, length or maybe height. Let us just consider height. It increases to 9 times. Means it becomes 9H. Now I think you must be having some idea for that. So sigma is equal to rho Vg by area, and linear dimension increases by factor 9. That means here height, or you can say L, or maybe whatever, one dimension increases, which is not bottom, 9H. So considering increasing height only, volume increases only 9 times, because see here, mass, new mass, the giant mass become rho L B H is 9 times H. So volume, or you can say simply mass. Let us just consider volume. Volume, kamkar. So volume of giant become 9 times volume of when it was tiny one. So put this value here. V become 9V. V become 9V. Sigma is equal to 9V rho G. If you compare with sigma, so sigma increases 9 times. Sigma increases 9 times. We have example number 10. I think you should pause the video and why don't you solve this example by yourself? We have solved many examples now. So example number 10, a steel wire of diameter is given, D diameter 2 millimeter it is given, so we need to convert this into meter. 2 multiply by 10 power minus 3 meter, that we know has a breaking strength. That means to cut the object. Yes or no? Yeah. A breaking strength is given 4 multiplied by 10 power 5 Newton. So it is a force is given. See, sometimes breaking strength is also used for sigma. So you have to understand the context for that. But as of now, it is given breaking strength for the force F is equal to 4 multiplied by 10 power 5 Newton. The breaking strength of similar steel wire of diameter. So if we change the diameter, let's say this is D1 and this is D2. D2 become 1 millimeter. So what will be breaking strength? What should be the force for that? Oh, it's a very simple. So yeah, we know that D1 is equal to 2 millimeter. F1 is equal to 4 multiplied by 10 power 5 Newton, that is given. And we need to identify F2 if D2 is equal to 1. So we have stress is equal to sigma is equal to force by area, and these are not required as of now. So just ignore these equations. Don't worry. So wire is similar, thus stress must be equal. See, it is mentioned that steel wire of diameter 2 and both are similar. Both are similar. Means sigma, it is similar. So sigma is equal to, we can put F1 by force by area. Sigma is equal to force by area. So F1 divided by pi by 4, D1 square is equal to F2 pi by 4. So can we cancel pi by 4? Yes, of course. So F1, can we put D1? D1 is equal to 2 multiply by 10 power minus 3 square. So can we say is equal to 4 multiplied by 10 power minus 6, and D2 is equal to 1 multiplied by 10 power 3 square is equal to 1 multiplied by 10 minus 6. So can we just 4? So it becomes just, it will be cancelled. So it will be 4. 1. So can you have answer? F2 is equal to F1 by 4. You just need 1/4 load. You just need 1/4 load to break the same wire. If you take 2 millimeter wire, that means it is having fourth time capacity. It is having fourth time capacity. So just divide by 4. Divide this capacity by 4. So it becomes 1 multiplied by 10 power 5 Newton. Oh, C answer is the correct. Or you may also solve like that. Force is directly proportional to diameter, or simply we can say sigma is equal to force by area. If sigma is constant, so we can say force is proportional to area. Force is equal to pi by 4 d square, means proportional, means force proportional to d square. Here d is 1 half, so F become 1 by 4. That is our answer. A is equal to, answer is equal to 1 multiplied by 10 power 5 Newton. We have example number 11. A light rod of length L is suspended from a support horizontally by means of two vertical wires A and B of equal length as shown in figure. So see, first statement, it is a given just a statement and the drawing is given. So directly you can read the drawing and you can get the idea. If it is not given, if suppose drawing is not given, at that time you have to make your drawing by reading the statement. It is somewhat difficult, but you have to learn that. So here this is a road, means a metallic road having any shape, cross section area we don't know, having length L, and its somewhere here mass is attached here, and having TA. Because of that, there is a tension in the tight side, or you can say simply having wire A is here, wire B is on the opposite side, and because of that, it is having some stress inside it. So here, then it start like that from this the cross sectional area of A. So area of A, let's just assume cross section area of A. The cross section area of A is half, so we can say equal to half of B. That means A of B by 2. And the Young's modulus of A. What is Young modulus? Don't worry at all, but just write Y. It is defined as a Y. Y of A is twice of. We can write Y of B or small. Fine. A weight W hang. So weight, it is hanging here. Weight is hanging here as shown. The value of X. That means this is the X value of X. value of x, so that W produce equal stress. Here it produces sigma A equal to sigma B in wire A and B. So such that x should be L by 2, x should be L by 2, L by 3, 2L by 3 or 3L by 4. Good question. So here LA is equal to LB, AB is equal to AB by 2, that we already derived. YA, what is YA and YB? Don't worry at all. Here it is mentioned sigma A must be equal to sigma B, as stress is equal, right? It produces equal stress. That means sigma A is equal to sigma B. What is sigma? Stress is equal to force by area. Stress is equal to force by area. See here sigma is equal. That means FA, sigma A is equal to sigma B. For A, we can write FA by AA, FB by AB. Do we have areas? Value of areas? Yes. AA, AA is equal to AB by 2. Just put AA, AB by 2. 2 should move opposite upper side. Can we cancel this AB, AB? Can we cancel this AB, AB? Right. So become what become? Here 2FA is equal to FB. That is, let's put this equation number 1. Then see, system is in equilibrium. It is not moving. So we know that we can take moment. We know that vertical forces are constant, horizontal forces are constant, and summation of vertical forces are 0. Summation of horizontal forces are 0, and summation of moment is also 0. We know that algebraic sum of an object, if it is in equilibrium, it should be 0. So let's take moment about point C. We are taking moment about point C. So see here, there are, we can see here that is the case. This object upper side TA is upper side, or simply it generates stress. TB is also upper side. We can write in place of TB, we can say force because of string A, force because of string B. See FA taking moment about C. So this is moment with respect to this. FA clockwise multiplied by distance x. FA multiplied by distance x and is equal to opposite direction. This is having opposite direction, anti-clockwise. So what happen? F, this is B, FB, this is B, multiply by distance. What is distance? This distance, this distance. So can I say L minus x? So mention here FAX minus FB L minus x is equal to 0. So this is taking, we are taking moment. We already learned this, how to take moment. FBL, FB, can we say FB is equal to FB is equal to, from here, FB is equal to FA? Yes or no? Yes. So we can remove this. And therefore, here x minus 2L plus 2x, so become 3x minus 2L. So x is equal to 2L by 3. X is equal to 2L by 3. Do we have answer? X is equal to 2L by 3. Answer C is correct. And you can see here, this is just an additional information to just make you confuse, but it was not required. This is just an additional information. It is given Young's modulus. We will study this Young's modulus, but this is just an additional information. So don't get confused with the additional information which are given. So answer C is the correct answer. Let's have one more part, that is a strain. So see, if we apply force, we know that increase, there is an increase of length, and there is a one more measurement is available, and it is known as the change in the length to the original length. It's a ratio of change of length. That means see, initially it has L length, but if we increase this length, so it become delta L. It become delta L. So there is an increase of length. So it is length, change of length. It is a ratio of change of length to the original length L. See, this is increase of length. It is taking along the force, line of force of action, and therefore it is also known as longitudinal or a linear strain. See, there may be name of longitudinal or linear strain. You should remember both longitudinal or linear strain. So the strain is perpendicular to the applied force is called lateral strain, but don't worry, as of now we will study this again. Just remember this: strain which is perpendicular to the applied force, right? So force is applied here. We consider longitudinal linear, that is along the axis, but if it is perpendicular change, means change in the diameter. So that is given by delta d by d. We will study this. Just wait. So example is given here: a copper rod 2-meter length, so L is given 2 meter, is stretched, that means delta L, change of length, stretched by 1 millimeter. Delta L is 1 millimeter, and the strain will be, options are given, right? And it is volumetric, or if it is not, we will study. Don't wait, don't worry at all. What is volumetric that you don't know? Fine. We will take this question again. So L is equal to 2, delta L is equal to 1 millimeter, and it is 10 power minus 3 meter. Thank you very much for watching Physics Doctor.